Okay, thank you very much. I'd like to thank Gez and David for the invitation to this very nice workshop. So I'll talk about the problem on whether a Gabor frame in finite dimensions possesses the full spark property or not, meaning that whether we have non-trivial linear dependencies among the elements of a Gabor frame. And even though I'm not expert in applications, this is could be particularly good for recovery problems. The higher the spark of your frame, the better recovery you have. So it would be nice to have some algebraically constructed frames that you don't have to check what their spark is. Okay, so we use the usual notation. We have the cyclic shift, or you want the time shift operator, T, that basically pushes all the coordinates of the vector one place to the right, and the last one becomes the first. Modulation operator, you just multiply pointwise by a certain character. Okay, so omega here is the nth root of unity. So these two operators commute, as we've seen. They commute up to a phase, and they generate the so-called Weyl-Heisenberg group. Okay, I guess these are things that everyone knows here. So for the linear dependence questions, we just drop the phases. Okay, so basically we have, as we call it, a projective representation of Zn squared. That has some nice properties like irreducibility, for example, but this will not be used here. So we just focus on the representatives. Okay, so we have modulation, power of the modulation operator times composed with a cyclic shift operator. And this is what the Gabor frame is. The Gabor frame is the set of all time frequency translates of a certain window function. Okay, so we have n squared vectors, okay, in an n-dimensional space. So we can take also subsets. Usually we'll take subsets of n elements, okay, and thus whether these are linearly dependent. Okay, so phi comma lambda is just the time frequency translates for which this pair kappa lambda belongs to this this set lambda here. And the question that I will answer this in this talk is whether there are windows phi such that the Gabor frame generated by this window has a full spark, meaning that every subset of n vectors is linearly dependent. It's a basis for our space. Okay, so of course it doesn't make sense to ask whether all of them are linearly dependent. They are not. So this can be thought as the discrete version of the so-called HRT conjecture, which is still open. But this is about L1 functions on the real line. So the progress briefly on this conjecture for n prime, that problem was posed and solved by Lawrence, Gutzfander, and Walnut. For several few small dimensions was verified by Kramer, Fander, and Raskov. And I'd like to talk about this 8-dimensional thing. That was actually a SIC-POVM in 8 dimensions that didn't have any linear dependencies. It was proven by Appleby, Bengtson, Blanchfield, and Dang. And that was how I got introduced to this problem by Professor Bengtson, actually. And we will see the proof for all n here, regardless of prime or composite, and actually an explicit construction of window functions that give you full spark Gabor frames. Okay, just a little bit about the signal recovery. So this full spark Gabor frame, well, it's called a frame because it spans the whole space, but it has some other nice properties. So it is equal norm, of course, because all these operators are unitary. So every vector here has the same norm. And it's also tight, okay? So somehow it imitates the properties of a orthonormal basis. Okay, so if you project F, take the squares of the projections, then you take a certain multiple of the norm, the L2 norm of F. So if it has this nice property, the full spark property, it is also called maximally robust to erasures, meaning the following. So if, let's say that you want to transmit somehow the vector f, okay, and you do it by the following means. You just take the inner product with respect to any vector in your Gabor frame, phi sub k. So as long, so we assume that we have a channel where some information is lost, okay? So some of these inner products are lost in the way. But as long as at least n of them are survive, then you can recover f, okay? You can recover f by constructing a dual frame to these remaining vectors. This formula can reconstruct f, regardless of which n of them survive, okay? So if n is fairly large, then you have n squared bits of information. As long as just n of them survive, then you're done. So you have, this is what means maximally robust to erasures. And the only algebraic construction that, well, I personally know were the harmonic frames. So basically you take the DFT matrix, you chop off the first few rows, and the columns of this matrix are, is a frame with the same property. So it's an equal norm tight frame, maximally robust to erasures. Full spark means that every subset of n elements here is linearly dependent. That's the full spark property, okay? And also for operator identification in compressive sensing, so let's say that you know that a vector f is, can be written as a linear combination of few elements from a Gabor frame of phi. In other words, I identify this set of operators, linear combination of at most s time frequency operators. So assume that you have such a representation. So if you write it as sum of s, linear combination of s time frequency translates of phi, then you know that this is unique, right? As long as s is less than n over 2. Because if you had two different representations, that would give you a linear combination of 2s vectors, a linear dependence between 2s elements of this form. But if you have, you cannot have that if you have full spark, okay? If your window phi generates a full spark Gabor frame. Okay, so this is just as an aside. So this is actually got to learn more first about this problem and then about linear dependencies. So again, this is a similar, I mean, it's on the same object, but different question whether we can achieve equiangularity between these vectors. And as an aside, I mean, I think that there's some work whether equiangularity and full spark are somehow connected, even when equiangularity is present. So what Appleby, Bengtson, and co-authors proved is that, among others, of course, that in some SIC-POVMs in dimensions 3 that are square free as well, dimensions divisible by 3 that are square free, then these SIC-POVMs always have linear dependencies. Okay, that's one consequence. For other dimensions not divisible by 3, it's not clear. For example, in dimension 8, you have full spark, equiangular, maximal equiangular tight frame that's also full spark. So that's also, I mean, an interesting aspect about whether there are possible connections.
So for 8 we know one which is full spark and SIC-POVM.
Yes.
Is the only one we know, or is there also one for 16?
The only one that I personally know, that I don't know whether the other ones have any obvious linear dependence relations. But if, for example, this conjecture is true, odd dimensions of that are multiples of 3, you always have linear dependencies. Yeah, that's actually. But the others, it's not. I don't know. Mm-hmm.
But it is established that for the SIC-POVM in dimension A, where we do have linear independence, which is what you just said.
Yeah, I think that was numerically right.
Yeah,
that was yeah. Okay, so let's say about the idea of the proof. So as I said, so I'm taking not a subset of n time frequency translates and check whether the corresponding vectors satisfy some linear dependency relation. So you can form this n by n matrix. Okay, we will see examples. So you take this n by n matrix denoted by d sub lambda. Okay, taking this particular n time frequency translates. And then you take the determinant. Okay, basically, you want to prove that every such determinant is non-zero. So this determinant is a polynomial in terms of the coordinates of your vector. It's with some certain additional properties. It's a homogeneous polynomial of the n variables of degree n. So at the outset, we know that we have one of these two extreme cases. So if one of them, just one of these determinants is zero, then you can never have zero as a polynomial, okay? You can never have full spark. But if all of them are non-zero, then just take your window to avoid the zero set of this finitely many polynomials, which is still has measure zero, okay? So either almost all windows generate full spark Gabor frames, or no window can generate Gabor frame. And we will show that all these determinants are non-zero as polynomials. Okay, so these are some examples. So you just form this n by n squared matrix of the time frequency translates of your vector z, and you take all n by n submatrices, and you want to prove that they're non-zero polynomials. And what we'll do from now on is that we will try to distinguish the columns that have the same time shift. Okay, so like here, so first we put the columns that have no time shift, then z naught is shifted to the first row, and then z naught is shifted to the second row. This is what we'll do in all matrices. So we have some sort of canonical order how to write the columns. So for example, this 2 by 2 matrix that corresponds to this time frequency shift is this one, z0 squared plus z1 squared, non-zero. Okay. Another example here. So basically, how do you prove that this, you expand this determinant, and what is the technique I'll use here? Which is the same technique that Lawrence, Funder, and Walnut used. You just try to find one single monomial that appears in your expansion of the determinant and prove that the coefficient is non-zero. You have to somehow be careful, try to find the total contribution that has this monomial here, and prove that it's non-zero. So for several monomials, this is easier than others. So in order not to get this heavily loaded, order 2, what? Or
why is it? I know that's
it's squared, yes. Yeah. It's homogeneous of degree equal to the dimension. So okay, I'll just try to convey the idea of the proof through an example, a particular 6 by 6 matrix. I choose 6 dimensions because it's not prime and it's also large enough in order to understand a couple of things. So how this polynomial, these determinantal polynomials look like. So you take several 6 time frequency shifts of your vector z, and you form this matrix. And as I said before, you group the same, those that have the same time shift together. So first you have no time shift, then the next 2 columns have time shift, so z naught is shifted to the 4th place. And the last column has z naught to the 5th place. Or you can see that z naught has a decreasing somehow place in the column. Okay, so this is a canonical way to write your matrix. So let's try. So how do you take the determinant? So basically you take all possible diagonals. Okay, generalize. You multiply all the elements with a sign, plus or minus sign. Okay, that's the formula for the determinant. So let's see what happens when we multiply the elements from a diagonal, and then try to see what's the contribution to the determinantal polynomial. So let's take from the first 3 columns here, have the same time shift, a 3 by 3 minor, a minor of maximal size. Okay, so let's take the first 3 rows. Then from the next 2 columns, let's take 2 by 2 minor. But you don't want the rows to overlap. Okay, so you take different rows in every submatrix. And here you just take 1 element. Okay, so you have this diagonal union of blocks, and we try to see what happens with the diagonals contained in this union here. Every diagonal, what we observe first, that every diagonal gives you the same monomial with some coefficient, but we'll deal with a coefficient later. For example, if you take the main diagonal and you multiply all the elements, you get z naught 3 times, z naught cubed, and then you get z1, z2, and z5. Okay, so you get this monomial with some coefficient. So here should be omega. Omega is the 6th root of unity here. If you change the diagonal, as long as you stay in this union, you still have the same monomial. So you ask, what is the contribution? Okay. Another observation is that in order to get the determinant of d sub lambda, you take all the possible diagonal union of blocks this way. Okay, so we'll see another. For example, let's take this 3 by 3 minor from the first 3 columns, then this 2 by 2, and this element here. So we get a different monomial. You see, no matter what your diagonal is, you get this monomial, z0, z1, z4, z5 cubed. And the reason is simple, because if you take the part of the diagonal that stays in this 3 by 3 matrix, you get 1 times z0, because the first row is only z0, right? 1 times z1 and 1 times z5. Okay, so no matter what your diagonal is restricted to this 3 by 3 minor, you get the same monomial. Now, what about the total contribution? Okay, so this is just the formal definition. What happens? This situation carries on to the general case for all dimensions n, no matter what your time frequency translate is. Okay, so as long as you write your matrix this way, so this is what I mean here. First, you write the columns that have z0 at the 0th row, then z0 to the first row, and so on. And you take correspondingly the so-called diagonal union of blocks in the same way. From each submatrix, you take a maximal minor, and you want this to have rows that do not overlap. So you sum over all this diagonal union of blocks, and this is your determinant. So, well, yeah, I'm using some notation here I have to explain. So all the diagonals of a matrix can be put into one-to-one correspondence with a symmetry group, okay? Symmetry group of n elements. So here, just because we're taking not exactly. We're taking a quotient subgroup. Okay. So anyway, I index this monomials by some element in the permutation group. So for example, for the first example I've shown, okay, where it contained the diagonal, the main diagonal, what's the total contribution to this specific diagonal union of blocks? You just take the product of these three matrices, or the determinants of these three matrices. It should have a sign, but we'll see that the sign is not important because we'll have to determine whether it's non-zero or not. So from this product of these three determinants, you can factor out the monomial, okay, which I will denote by this capital Z of iota. So what remains when you factor out all these variables here, just minors of the Fourier matrix, of the DFT matrix, 6x6 matrix. In this particular case, it's non-zero, okay? So this is one first observation. For the other example that I have shown before, for this choice of diagonal union of blocks, you just multiply again these three determinants in order to get the contribution. And it corresponds anyway, somehow to this cyclic permutation of these elements.
Do you know?
Yeah.
Do you know that that particular monomial only appears in that single?
Yes, that's the important question. I mean, the important question is whether these monomials, whether there's a one-to-one correspondence between monomials and diagonal union of blocks, or if different diagonal union of blocks gives you different monomials. And that's not always true. That's where the difficulty of the problem is. For example, here's the coefficient. This is not the total coefficient of this monomial, but the coefficient for this particular contribution, okay, this particular diagonal union of blocks. This monomial could possibly appear in a different diagonal union of blocks. So you have to take into account that coefficient as well. So we are interested, however, in monomials that have this property that you mentioned, that appear in a unique diagonal union of blocks. So if such a monomial is obtained from a unique diagonal union of blocks, then the coefficient, as we've seen, is a product of Fourier minors. And these are more convenient to work with because you can more easily determine that coefficient is non-zero or not. Okay. Because it's a product of Fourier minor, so you just have to check whether each such minor is non-zero or not. And otherwise you would have sum of products and it would be more difficult somehow. So this was the technique of Lorentz, Funder, and Walnut in the prime dimensions. So they proved, they had some very nice combinatorial argument that such monomials there are always such monomials obtained in a unique way. In this terminology, from a unique diagonal union of blocks. In particular, what they showed is the following. So if you arrange your variables in a lexicographical order, Z0, Z1 up to Zn minus 1, then the monomial that appears first in this lexicographical order appears uniquely. Okay. And this fact, coupled with Chebotarev's theorem that every minor of the prime dimensional DFT matrix is non-zero, okay, this gives you the fact that when your dimension is prime, almost every window gives you a full spark Gabor frame. Okay, because you take, for example, any n time frequency translates, and this determinant has a monomial that appears from a unique diagonal union of blocks, and therefore its coefficient is a product of Fourier minors. So it's non-zero. Okay, so every such polynomial is non-zero. And how do we extend this in the general case? It turns out that there is an abundance of monomials appearing uniquely, but still the difficult thing is to see whether each of the Fourier minors is non-zero, because when n is composite, there are obviously some zero minors, right? So I focus on different monomials, so-called, I call it consecutive index monomial. So from the setting that I've told you before, so writing first the columns that have no time shift, then those that have shift equal to 1, you just take the diagonal union of blocks that contains the main diagonal, okay? So this monomial appears uniquely. But this is the hard part, to prove that it appears uniquely. The easy part, once you know this, is that it has a non-zero coefficient. So if it is obtained uniquely, then the coefficient is a product of van der Monde determinants. Well, Fourier minors, but of a specific, particular kind, van der Monde determinants, up to some phase, of course, which are non-zero because they correspond to different phases. So let's see our basic example again. So I repeat that this situation carries out for all dimensions n for any time frequency translates you consider. So you take this diagonal union of blocks that contains the main diagonal, and you see that if you factor out your monomial, what you're left with is a product of van der Monde determinants, simply because you're taking consecutive rows, meaning that in the corresponding columns you have successive powers of a certain phase, or geometric progression, if you like, which is the definition of the van der Monde determinant. Here you might have to factor out some phase from each column, but at the end you have product of van der Monde determinants times a phase. And they correspond to different, these van der Monde determinants correspond to different phases, so they're all non-zero. So the hard part, I mean, there were two hard parts in this problem. First, to find good candidates for monomials that could possibly give you non-zero, and then prove that they appear uniquely. So how do we prove that this appears uniquely? I will not go into the technical details of the proof. I understand it's after lunch, so I will just show a picture. So this is the identity permutation. So the monomial that we got from this main diagonal was this one, z0 cubed, z1, z2, z5. So let's arrange the indices in a cyclic manner and see what's the occurrence of each index. So 0 appears 3 times, 1, 2, and 5 appear once. If you take different diagonal union of blocks, or different permutations if you like, you get a different distribution of indices. So you see here that if you take a different one, these indices start to move away from each other. So here 0 appears 3 times, 1, 3, and 4 appear once. And similarly, if you just take another one, you see that that may lead you to think that they are not, in other diagonal union of blocks, the indices are not concentrated around a specific index. So how do you quantify this? This looks like a random variable having somehow a minimal variance, being concentrated around a mean value. So the random variables that I associated with these monomials are the ones that basically record the occurrence of each index. So for example, let's say that to z sigma, to this monomial, we associate a random variable as follows. So if this monomial you have is z0 to the alpha naught, z1 to the alpha 1, and so on, then you just take the probability of x sub sigma to be equal to I, just alpha I over n, okay? So these monomials have degree n, so that the sum is equal to n, so this is a well-defined probability somehow. So what happens with the mean value, the mean squared value? So it's not, I didn't prove that the variance, but the second moment is minimized. Of course, one has to be careful because the values of the random variable are taken modulo n. So you have to somehow embed this to the real numbers. So for example, you take this distribution here, and what we do is we take, for example, 5 to 0, 0 to 1, 1 to 2, 2 to 3. So you want this support here to be connected in integers. And you want, of course, the first one to be 0. So under this technicality, under this mapping, we have the following fact that the second moment is minimized uniquely, which means that only the diagonal union of blocks has that minimum value, gives that minimum value for your expectation here. And all other diagonal union of blocks give you strictly higher expectations. So this proves that this monomial appears uniquely. Okay. And this is in any dimension, in every n by n minor, n by n submatrix of this short time Fourier matrix. The consecutive index monomial, this is obtained uniquely. And this is the reason that I told you before, the concentration of indices is maximal possible, quantified by this mean, by the second moment of this random variable. And this proves that for any n and for almost all windows, the Gabor frame with window phi has full spark. And the good thing about the minimum, the fact that this consecutive index monomial is minimized, is uniquely minimizes the mean, the second moment, also gives you some nice construction. So, for example, if you take any xc to be a transcendental number or an algebraic number whose degree over this cyclotomic field is high enough, sufficiently high, then this vector here, which resembles like a Gaussian, if you like, so it's 1 xc, xc to the fourth. In general, the ith coordinate is xc to the I squared. Okay. So this generates a full spark Gabor frame, and you can make this more specific. You can take zeta to be, for example, a primitive root of unity of order n minus 1 to the fourth. This thing here generates a full spark Gabor frame. So we also have an explicit construction of such Gabor frames. And what I'll talk about in the last few slides is the non-cyclic case. So what happens if the translations, or if you want the coordinates of your vector, are not indexed by the cyclic group of n elements, but some other abelian group of order n. And as modulation operators, take the pointwise multiplication by characters of this group. So what happens? And I proved recently this one, that you have the exactly the opposite situation. So if G is a finite abelian non-cyclic group, then we can never have full spark Gabor frames for every window. And as I told you at the beginning, we have either one of the two extremes. Either no full spark Gabor frames exist, or they exist for almost all windows. So here we have the other extreme. And I will just show you the proof when this was already known for the Klein group, Z2 cross Z2 by Getzfander, I think. And so let's see, for example, a proof. What's the technique when G contains a subgroup isomorphic to the Klein 4 group? So it's not hard to show that this property, the full spark property, is hereditary. So if it's true for some group G, it is also true for all subgroups. So that's one way to argue. Another way to argue that's more perhaps illuminating for the proof, the general argument, is take an arbitrary window phi f and try to construct somehow a vector that is orthogonal to too many time frequency translates of phi. Okay. So for example, take in window f here. Okay, so G contains a copy of as a subgroup contains a copy of the Klein 4 group. And then f bar, so that take the complex conjugate in every coordinate, is orthogonal to to any time frequency translate of f of this form. So m sub c t of a of f. So for any a belonging to this Klein subgroup, not the identity element, and xi in the dual group that satisfies this property, xi of a is equal to -1. Okay. And you can see why this inner product is non-zero. So this time frequency translate is xi of evaluated at g is xi of g times f of g minus a. So this is the time shift, and this is the pointwise multiplication by the character here. And of course, we multiply by f of g. And we'll see why this sum is equal to 0. If you replace g by g plus a here, so this f of g minus a times f of g becomes this one, but plus a is equal to minus a. It's an element of order 2. So you have, again, f of g minus a times f of g. But on the other hand, you have xi of g plus a, which is written this way, and xi of a is factored outside. So you end up with minus your original inner product. So this has to be 0. And how many time frequency translates of this sort exist? There are at least three elements A of order 2. Okay. And for every such A, there exists n over 2 characters xi with this property. Okay, because if you just take the character restricted on the cyclic group generated by A, this is the non-trivial character. And it can be extended to n over 2, the index of these two groups, to n over 2 characters with the same property, xi of a is equal to -1. So in total, there are 3 times n over 2 time frequency translates that are orthogonal to f bar. This could also give you some good bounds on the support of the short time Fourier transform of f. So something similar you do in the general case, but it's, well, notation is, I mean, you need some notation first. I'll just briefly show what is the, so if you have any window z, so as I told you, it suffices to prove that this doesn't hold in any group of this form, z mod pz cross z mod pz, okay, where p is a prime. So what you do for your arbitrary window z, you just arrange it in as a square array, okay? So theta here is just an element of fp squared that doesn't belong in fp, okay? So these are your elements here. And if you write it as a matrix, then the vector that is orthogonal to too many time frequency translates is just the conjugate transpose of the inverse matrix. So it turns out that it is orthogonal to at least 2p squared minus 2, which is much larger than p squared time frequency translates of z. And this proves that you can never have full spark probability when the underlying group is non-cyclic. So that was all. Thank you very much. No, not exactly. I mean, for example, I'm not using like an independence result, you know. But for me, it was more easily translated into the setting of random variables because it had a feature that, you know, as I mentioned, resembled a random variable that has small variance, and this is what I tried to prove eventually.
So then, again, what is the role of the randomness? Can you just maybe identify that the concentration features are analytically and say this is unique to this particular term in the monomial determinant? So it's kind of, it's a bit of a vague question, but what is the role of randomness there, right? I mean, a measure of peakness, I guess we can identify with something.
I don't know, for me, it was a more convenient way to express it because that's how I understood it. I mean, I could just say that it is to take a monomial that minimizes certain this quantity. That's it. So.
Is the quantity
Yeah.
It's just
Yeah, exactly. I mean,
elegantly written here as a pairwise, so there's no randomness that appears.
yeah, exactly. Yeah.
Yeah, but it's still.
I mean, we also, this, in the paper with David Wong and also from Pilot, we also gave an outline of the proof, and I think without randomness.
Yes, exactly. I mean, you can say that a certain quantity is minimized, and you don't have to mention random variables at all. I mean, it's.
You can write down this thing deterministically, and you can say whatever, you can calculate this expectation, write it down, say this quantity is minimized for this, but then it's like, okay, what's this? So it's more like,
This may be a very naive question, but your proof uses a very nice intuitive way to prove that a determinant of certain distances away from zero, right?
What did you say? Bounded away from zero, you said?
Yes, because I mean, this is what you do with your number.
I just proved that a certain coefficient, that there are coefficients that are non-zero, but I didn't prove any bounds. I mean, how big these determinants are.
But do you think similar strategy would work if you replace determinant by determinant?
I don't know. I haven't thought about it, but so for example, I don't. Is it?
I know it's useful, but I just know determinants are not objects.
Okay, so what are the, if you consider the Fourier matrix, I guess it's about this I want to see whether, for example, prime dimensions, do you have permanent, the submatrices, square submatrix of the Fourier matrix, are they non-zero? Which is interesting, because this is still a sum of roots of unity. So when the dimension is prime or a power of a prime, I mean, the theorem, it has to be somehow union of p cycles. But yeah, I haven't thought about it, to be honest. So.
I mean, and I know that I'm going to ask this now, and then I'm going to forget it, but I know that I can ask my students and they will remember. So again, the game about SIC-POVM versus full spark. So in dimension A, are there also linear dependent ones, or but the only one which is known were there. So on all the fiducials known for a dimension less than 8, or are there just some known or something?
I think almost certainly, yes.
And they